Good afternoon, this is Bill, continuing our discussion of discrete mathematics. Today we begin on Chapter 4. Chapter 4 deals with number theory. Very interesting chapter. I hope you enjoy it as much as I do. So, number theory, and we're going to start off with what is probably a review here, just some notation about some different sets of numbers. The first set that I want to talk about, it's sometimes written this way as a script n like that, and this is the natural numbers. And this is equal to the set that looks like this. And it goes on all the way up to infinity. So please send me an email when you get there. The other set that we want to talk about here are what are called the integers. And again, we use a z to denote that. That comes from the German word zahlen, which means to count. These are the integers. And that looks like this. It starts off at minus infinity. And then goes up to infinity. Again, you'll notice these are whole numbers. Just a little bit of review here. We will notice that the natural numbers are a subset of the integers, so sometimes we'll write that this way. We'll say that n is a subset of z. Okay. The other next one that we talk about are these things called q. And q refers to the rational numbers. And that's equal, I'm going to use a different notation here, and that's equal to the set of all a's divided by b such that a and b are elements of the integers, like that, and b doesn't equal 0. Remember, dividing by 0 is not defined. So it's much harder to make a list of these things, but this is going to include numbers like 1/2 or minus 7 and 9/16. Stuff like that. It also might include numbers like this if I were to write 0.29, when we know that 0.29 is equal to 29 over 100, or 0.316, that's equal to 316 over 1,000. Again, notice that this is an integer divided by an integer. But now what may not be clear to you is, what about a number that looks like this? Suppose I have a number that looks like 0.213, 213, 213, and what I'm going to do is I'm going to write a line over this to indicate that this keeps repeating forever and ever and ever and ever. Now, my claim is, and perhaps you've seen this, this is also a rational number, although it's not obvious what rational number it is. Well, we're just going to resort to a little trick here, and we can figure it out. I'm going to call this number x. And what I want you to note is that it keeps repeating after 3 digits. So what I'm going to come over here is if this is x, then what's going to happen is 10x is equal to 2.13213, and again, that repeats. And if I come over here and I get 100x is equal to 21.3213, and that repeats. And I get that 1,000x is equal to 213.213. And that repeats. So what happens over here is I want you to notice the following. If I come over here and I go 1000x and I subtract 1x, well, this is equal to 213.213213, and x is equal to 0.213213 repeating. And I come over here and I do the subtraction. Well, 1000x minus x is 999x. And that's equal to, now when I come over on this side, everything on the right side of the decimal point cancels out. So I'm left over here with 213. And now what I can do here is I get that x is equal to 213 over 999. And I note that 213 is an integer, 999 is an integer. So from this, I conclude that x is a rational number. Like that. Okay? Now, what's not so obvious is if I have a number that looks like this. Suppose I had 0.01001 0001. In other words, notice over here I have 1 0. Over here I have 2 zeros. Over here 3 zeros, 4 zeros, and this keeps going on. This pattern keeps increasing. It turns out that this number over here is not a rational number. Okay? No matter how many tricks I try to do, like I just showed you on the previous example, I'm not going to be able to express this in the form a over b, where a and b are both integers. Although it's not obvious that that's the case. Okay? But it turns out that we have another set of numbers that we have to consider, and that's this set called R. These are the real numbers. And the real numbers, it's a little bit harder to write down what they are. Well, they are the rational numbers, like the ones we had before. Union, and I'm going to write over here, we're going to introduce a new symbol here. I'm going to call it I. And I is equal to the irrational numbers. So what's an example of an irrational number? Well, this number right over here is an irrational number. What's another example of an irrational number? There's that funny number called pi, which we know is approximately equal to 3.14159. And it goes on. The square root of 2 is an irrational number, and we'll prove that a little later on in this chapter. But so now realize, so we have this thing called the rational numbers. So we have the natural numbers, we have the integers, we have the rational numbers, and then we have the real numbers. And we'll be talking more about these in this section. So we want to continue our discussion here, and the main topic that we want to cover here is this notion of what's called divisibility. Very simple idea. And we're going to restrict ourselves. We're concerned with integers here. That's it. And we're going to start off with a definition, and we are going to say that an integer a divides an integer b That's an over there, in case you couldn't tell. If and only if there exists another integer k such that Okay, so we're saying that A divides B. So it would be such that B is equal to KA. Okay, so for example, okay, we would say that 3 divides 6. Why? Well, pretty simple. Because 6 is equal to 2 times 3, and 2 is an integer. Okay, that's pretty simple. So mathematically, we state that as follows. We would say that A, and here's the symbolism for it. We just draw this vertical line. We say A divides B if and only if there exists an integer K such that B is equal to A times K. Otherwise, we would say this. We would say A doesn't divide B. So to give you some examples, 3 divides 15. We would have that 7 divides 21. We might say that 13 divides 39. Okay, this is true because 15 is equal to 3 times 5. This is true because 21 is equal to 3 times 7. This is true because 39 is equal to 3 times 13. But we would say that 4 doesn't divide 15. Or we would say that 8 doesn't divide 21. Or we would say, for example, that 30 doesn't divide 39. Okay, with that definition of divisibility in mind, we can actually prove a couple of interesting facts here. So let me pose it as a question. Suppose I were to tell you that A divides B and A also divides C. What can we say about A dividing, and I'll put a question mark here, B plus C? Well, if A divides B, that means there exists I'm going to say there exists integer m such that B is equal to A times m. Okay? And if A divides C, that means there exists integer n, okay, such that C is equal to A times n. Okay? Well then, I notice the following here. I notice that B plus C is equal to AM plus AN is equal to A times M plus N. And I notice the following, that if M is an integer and N is an integer, then M plus N is an integer. So notice what I'm saying here. I'm saying that B plus C is equal to an integer times an integer. Okay? So the question over here, this question mark here, becomes yes. Absolutely. For example, if I have 3 divides 21, and I also have 3 divides 15, the question is does 3 divide 21 plus 15? Okay, and 21 plus 15 is 36. Does 3 divide 36? And the answer is yes. Okay, and I'll leave it as an exercise that if I'm given that A divides B and A divide C, does A divide B minus C? So let's turn our attention for a second to the Java programming language. I think you're all familiar with Java. And if I come over in a Java program and I declare a couple of integer variables, A and B, and I were to come over here and I were to say something like A is equal to 3, and I come over here and I say B is equal to 7, and I were to say something like the following. Let's just do a system.out.println A divided by B. Okay, now the thing that you need to remember about the Java programming language is that if I have an integer and I divide it by another integer, I've done A divided by B, okay, the result has to be an integer. So the question is what integer am I going to get over here? Well, if I'm dividing A by B, I'm dividing the integer A by the integer B. And I think you would be saying to yourself, you could take this back to your days in grade school. If I go 7 into 3, well, it goes in there 0 times. Okay? And in fact, I get 0 times 7 is 0, and I get a remainder of 3. Okay? So the output here is in fact 0. Okay? There is another operator in Java that you should know about called the modulus operator. And I would say A, and then I go %B. Okay, and this over here is the modulus operator. And think of modulus as meaning remainder. And again, for the modulus operator to make sense, the operators on both sides must be integers. Okay, and in this case, we're getting the remainder. So the output of this over here is going to be 3. Okay, so what I want to do is I want to get a little bit theoretical here. Let's get a clean page. There we go. Let's pick some different numbers here. Let's come over here and I want to pick some number A. I'm going to let A be 5 for a second. And I want to consider some integer B. Okay, and what I want to do is I want to consider what happens when I divide A into B. And I'm focusing in on the remainder now. Okay, now let's do something kind of clever here for a second. I'm going to come over here, I'm going to make a list of numbers. -6, -5, -4, -3. Okay, so here's a list of all the integers. And here's what I want to do. I want to take the number 5, and what happens if I divide the number 5 into 0? Well, 5 goes into 0 times with a remainder of 0. And if I come over here and I say, well, let's divide A into 1. Well, A goes into 1 0 times with a remainder of 1. And I think you can see the pattern here. A goes into 2 0 times with a remainder of 2. Goes into 3 0 times with a remainder of 3. Goes into 4 0 times with a remainder of 4. Now it starts to get a little bit interesting. A goes into 5 1 time with a remainder of 0. And I think you can see that what's going to happen here is as I start to repeat the pattern. Likewise, if I come back here and I go this way, like that. Well, this is kind of interesting. Notice what I'm doing here is, as you could say, that I'm breaking the integers down into 5 pieces. What I'm going to do, I'm going to come over here, I'm going to give these pieces a kind of funny names, and you should watch this very closely because this is not in your book. I'm going to have over here I'm going to have something, I'm going to write 0 here, and I'm going to put a little subscript there for 5. And I'm going to have 1, 5, 2, 5, 3, 5, and 4, 5. And over here, what I want is I want all of the integers that when I divide them by 5, I get a remainder of 0. Well, again, these are all infinite sets, but you can see this is going to be minus 5, 0, 5, 10, like that. And I come over here, and we can see over here, I'm going to get minus 4, 1, 6. Like that. And this over here is going to be minus 3, 2, 7. And I hope you're all starting to see a pattern here. Okay, and that's pretty interesting. A couple of things to note here. So notice that when I've taken 5 to be my divisor, okay, and I want to break these up into these sets of remainders, notice that I get 5 different sets, okay? Basically what we're saying here is that whenever we divide an integer by 5, it's going to have a remainder of either 0, 1, 2, 3, or 4. And what I've done over here is I've created these sets that contain, okay, this thing 0 with a subscript of 5. These are all of the integers, okay, that have a remainder of 0 when I divide by 5. This one over here, this 1 with a subscript of 5, these are all the integers that have a remainder of 1 when I divide by 5. These all have a remainder of 2. These all have a remainder of 3. These all have a remainder of 4. I stop over there. I don't have any more sets because I can only have, if my divisor is 5, I can only have 5 of these sets. Now I think you can see I can extend this to lots of other divisors. I don't have to just use 5. I could make this 23. And if I make this 23, if I were to say that A is equal to 23, then you could see that I'm going to have 23 of these sets. I'm going to have 0, 23, 1, 23, and it's going to go all the way up to 22 with a 23 in it. Okay, these represent the different remainders that I can get when I divide by 23. Notice that when I look inside of these sets here, again, when 5 is my divisor, that all of the numbers in here all differ by 5. Okay, now a couple of other interesting things can happen here. So I have a question here. What happens if I add an element from, let's say 2 sub 5 with an element from 3 sub 5. Well, okay, so here's the key thing to note. If M is contained in 2 sub 5, then M is equal to 5 times K plus 2. Okay, does everybody see that? Notice over here that if I were to divide this quantity right over here by 5, I get a remainder of 2. Now, if n, let's see, they said the other one is 3 plus 5. So if n is in 3, 5, then n, Okay, I used the letter K here. We must use another one over here. So I'm going to say 5j plus 3. Is everybody clear on that? So if I come over here now, I'm saying what happens if I add m plus n? Well, m plus n is going to equal 5k plus 2 plus 5j plus 3. Well, that's going to equal 5 times, well, I get k plus j. But then notice I add 2 plus 3. That's equal to 5. Well, wait a second. There's a little bit of a trick here. Notice that that's equal to 5 times k plus j plus 1. Which says that when I add these two elements together, I'm going to get something that has a remainder of 0 when I divide it by 5. So m plus n is contained in 0 sub 5. Well, that's a very interesting result. In fact, what you can do is you could really make up a whole table here. We could come over here and we could say 0, 5, 1, 5, 2, 5, 3, 5, 4, 5. Zero, 5, 1, 5, 2, 5, 3, 5, and 4, 5. And we could come up with an addition table for this. And the addition table for this is actually fairly easy to figure out. If I add together two numbers that are both divisible by 5, I get a number that's divisible by 5. In fact, 0 here is going to operate just like a regular old 0. Just think about it. If I were to take a number like 20, okay, 20 is contained in 0, 5. And I don't know, let's take a number out of 3 sub 5. Well, remember what this means. This means that if I divide it by 5, it's got a remainder of 3. So let's think of a number there like that. Well, that would be 18. Okay, if I divide 5 into 18, 5 goes into 18 3 times with a remainder of 3. So this is contained in 3 of 5. And if I add those two numbers together, I get 38. And according to my table here, that's going to be contained in 3 sub 5. Well, 38 is 7 times 5 plus 3. So that seems to work. Well, all of these other ones are going to work in exactly the same way. If I add 1, 5 and 1, 5, that's going to be 2. 1 plus 2 is going to be 3. 1 plus 3 is going to be 4. And let's think about 1 plus 4. Well, let's just consider an example here. If I have something contained in 1 sub 5, it's got a remainder of 1 when I divide by 5. How about 11? 11 is contained in 1, 5. And now let's take a number that has a remainder of 4 when I divide it by 5. Well, I don't know. How about 24? Well, 24 plus 11 is 35. And 4 plus 1 is 5. But 5, when I divide it by 5, has a remainder of 0. That's contained in 0, 5. So this is 0, 5 over here. Wow, this is kind of cool. So I think you can see the pattern here. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. But mod 5, okay, if I divide by 5, I get a remainder of 0. 2 plus 4 is 6. But when I divide 6 by 5, I get a remainder of 1. And I can just go ahead here and continue this here. So 3 plus 3 is 6, so when I divide it by 5, has a remainder of 1. 3 plus 4 is 7, that has a remainder of 2. 4 plus 1, that's going to be 0. 4 plus 2, 1. 4 plus 3 is 7, divided by 5 has a remainder of 2. And 4 plus 4 is 8, that's going to have a remainder of 3. And you can see over here, I've defined a whole table here of dividing by remainders. Okay, I think there's just one more point to make here. And that is the following. And this is a theorem, and I think intuitively we've seen this already. If a and b are integers, so if a and b are both contained in z, and b is greater than a, then b is equal to a times m plus r for m and r integers, and 0 is less than or equal to r is less than a. Okay, and again, you can see what that means. If I were to come over here and take a equal to, say, 7, and I were to have b is equal to 23, we're saying that 23, in this case, is equal to 3 times 7 plus 2. In other words, the remainder here is always going to be between 0 is less than or equal to r is less than 7. Okay, no matter what number this is over here, if I divide by 7, I'm going to get a remainder that's between 0 up to and including 6. If it's 0, that means that the number actually divides it. So if I'm using this number 7 here as my divisor, right over there, going back to our previous slide, right over here, we could create another table here that would go from 0 sub 7 all the way up to 6 sub 7. Okay? And I hope that that is all clear. Again, some of this is not in your book, so please, if you don't understand this, go back and review the video. Now, I want to talk about a problem that is in the book. They've actually worked through it, but before we do, I want to talk about some notation here. This is pretty standard mathematical notation, and I think we should just get a little bit comfortable with it. So what I want to do here is I want to pick some number. Why don't we pick n equal to 4? And you may recall in the last few minutes we talked about these different sets. I called them 0, 4, and 1, 4, and 2, 4, and 3, 4. But I want to, for example, come over here. I want to pick an example out of 2, 4. So for example, the number 6 is contained in this set 2 sub 4. Now, this is not standard notation. This is something that I've just made up here. But what is standard notation is we would say something like the following. We would say 6, and we use these triple lines here, and we would say this. Okay, and we would say this 6 is congruent to 2 mod 4. Okay, and I hope that everybody becomes comfortable with saying something like this. We're going to be using this notation quite a bit. Now, I hope it's clear that if we pick some n, if we pick some positive integer, okay, then we can talk about x being congruent, and I'm going to write question mark here, mod n. And the question is what can question mark be? Well, we know that question mark could either be 0, 1, 2, all the way up to n minus 1. Okay? Regardless of what this integer x is, we know that question mark can assume one of these n values right over here. All right? Now, let's return to a problem that's in the book. It's a very interesting problem, and it basically says the following. It says that any odd integer squared is congruent to 1 mod 8. And then you're asked the hard part, which is that you're asked to prove this. Okay, now everybody always gets very nervous when we see the word proof, and we'll try to show that this is not all that difficult, but let's think about it. Now, first of all, we're saying any odd integer. So here's something we should make concrete now, although I think you all know this by now. If n is odd, then n equals 2k plus 1. Not from, for some a, for some k. And likewise, if n is even, then n equals 2k. Okay, notice over here, odd number is going to be 2k plus 1. This is going to be even. In other words, if I look at my even numbers, 2 is equal to 2 times 1. Excuse me. 4 is equal to 2 times 2. 6 is equal to 2 times 3. In other words, even numbers are 2 times some integer. If I come over here and I look at my odd numbers, 3 is equal to 2 times 1 plus 1. 5 is equal to 2 times 2 plus 2. 7 is equal to 2 times 3 plus 1. I seem to be having problems here with arithmetic. 5 is equal to 2 times 2 plus 1. 7 is 2 times 3 plus 1. Okay, but you can see that in all of these over here are taking the form of 2k plus 1, and all of these over here are taking the form of 2k. So, what this seems to be saying over here, any odd integer squared is congruent to 1 mod 8. So this seems to be saying that 2k plus 1 squared is congruent to 1 mod 8. And we're asked to prove that this is always the case. Well, we're going to try the obvious, and we're going to see that the obvious doesn't quite work for us. So if I come over here and I say, well, suppose that 2k plus 1, well, that's an odd integer, and I'm going to square it, and that's congruent to 1 mod 8. And I come over here where I'm going to square the left side. So if I square the left side, I get 4k squared plus 4k plus 1, and that's congruent to 1 mod 8. And I go, well, I can cross out the 1's on both sides. And now I've got, it looks like 4k times k plus 1 is congruent to 1 mod 8. And I look at this and I go, what to do? And I have a confession. I don't know what to do. Actually, I'm quite stuck here. I think what's going on here is maybe I took the wrong approach to this, and I'm going to try something else. Now, what I want to recall is the following. You remember before when we divided by numbers? Well, here I want to talk about the integers mod 4. And it turns out that if I'm talking about the integers mod 4, remember that's going to be, I'm going to have those things called 0 sub 4 and 1 sub 4 and 2 sub 4 and 3 sub 4, which basically means these are all going to be integers of the form of 4k, for k an integer, and these are all going to be of the form of 4k plus 1, and these are all going to be of the form 4k plus 2, and these are all going to be of the form 4k plus 3. Well, let's look at a couple of things here. For any integer k, 4 times k, this is going to be an even number. And I leave it as an exercise for you all to figure that out. And I would also suggest that for any k in integer, 4k plus 2, this is also going to be an even integer. So I am going to claim that all of the odd integers are either of the form 4k plus 1 or they're of the form 4k plus 3. And I think that is going to help us get to where we want to go. So let's consider we have two cases to look at here. I want to talk about 4k plus 1 squared being congruent to 1 mod 8. And I also want to consider the other case, which would be 4k plus 3 squared congruent to 1 mod 8. And see what we can do about that. Well, I'm going to come over here and I'm going to square this side, and that's going to give me 16k squared plus 8k plus 1 congruent to 1 mod 8. And I'm going to cross the ones off on both sides. And look at what I've got left on the left side here. This is 16k squared plus 8k is congruent to 0 mod 8. Well, is that always the case? Well, notice over here I can factor out an 8. This is 8 times 2k squared plus k congruent to 0 mod 8. And I notice the following. If k is an integer, then 2k squared plus k is an integer, and 8 times any integer will be congruent to 0 mod 8. So that takes care of this case over here. I'm going to do the same trick right over here. If I go ahead and I square this side, I'm going to get 16k squared. And then let's see, I've got 12k, but I've got it twice, so that's going to be plus 24k. Okay, and I'm going to get plus, and when I square the 3, I get 9, and I go, okay, really? Congruent to 1 mod 8? I'm not so sure. But watch what happens here. I'm going to subtract 1 from both sides. So I get 16k squared plus 24k plus 8 congruent to 0 mod 8. Well, notice again what happens over here. I can factor out an 8, and over here I get 2k squared plus 3k plus 1 congruent to 0 mod 8. And I go, look, if k is an integer, then 2k squared plus 3k plus 1 is also an integer. So I have 8 times an integer, and yes, that is congruent to 0 mod 8. We've proved it over here. So we've proved it for both cases. We're done. The theorem is proved. Okay, let's turn our attention to something a little bit different here. I want to talk about prime numbers. I think you're all probably aware of what these things are. So we talk about, okay, an integer p is a prime integer if and only if I'm going to say 1 here, p is greater than 1, and number 2, the only integers that divide p are 1 and p. Okay. And the other so that's a prime number. A composite number that would be any integer that isn't prime. So to give you some examples, 7 is a prime number. The only integers that divide 7 are 7 and 1. 13 is a prime integer. 23 is a prime integer. But we know 24 is not a prime integer. 24 is equal to, for example, 6 times 4. It's also equal to 8 times 3. In fact, there are a lot of ways that I can multiply 24 out. So I hope that this distinction is very clear to you. Now, we are not going to prove this, but this is a property that you should be aware of, and that is every composite number has a unique prime factorization. Now let's talk about what that means. Let's give an example. Now I'm going to come over here. Let's look at the number 24. Now 24, for example, and we can do this in lots of ways, but we can come over here and we could say, well, 24 is equal to 6 times 4. And I note that neither 6 nor 4 is a prime number. So what I'm going to do, I'm going to come over here and I'm going to go, well, 6, well, that's equal to 2 times 3. And I note that 2 and 3 are prime numbers. Likewise, I come over here and I go, 4 is equal to 2 times 2. And 2 and 2 are both prime numbers. So I notice here that 24 is actually equal to 2 times 2 times 2. So that's 2 to the third. And over here, we have 3 to the first. Okay? This over here is the prime factorization of the number 24. And what this theorem says, and again, we won't prove it, but it says that this factorization is unique. In other words, if I were to claim that there's some other factorization here, q1 times q2 times all the way up to some q sub n, and this is raised to, I'm just going to say, some alpha 1, alpha 2, all the way up to some alpha n. And I were to tell you that these were all primes, what this theorem is saying is that the primes that appear here have to be these primes that I see here, and these exponents that I see up here would have to be these exponents right here. So let's just consider another number for fun. Suppose I were to come over here and I were to look at 98. Now I could come over here and I could say 98 is equal to, well, that's 2 times 49. And, well, 2 is a prime. 49 is not a prime, but 49 is equal to 7 times 7. So, oh, I think I'm done. This would be 2 to the first times 7 squared. And notice that both 2 and 7 are prime numbers. I've raised these to prime numbers. Okay? So you might want to try some numbers here just to have some fun. Let's do one more. We'll pick a big number just to see how this might work. So I'm going to come over here. What if I were to pick the number 1036. Okay, now I have no idea what the factorization of 1036 here is. Here's a little trick for you. If the last two numbers of a number are divisible by 4, then the entire number is divisible by 4. So this is equal to 4 times, and I don't know what 1036 divided by 4 is going to be. 2, and that's going to be 8. That's going to be 23, so that's 5, so that's 20. 36 is 9. So that's 4 times 259. Well, the 4 is 2 times 2. And now the problem is what about 259? Wow, I don't know. That might be a prime number. That might not be a prime number. Let's see what tricks I can pull out of the air here. Is that divisible by 3? Well, a trick for numbers being divisible by 3 is you add up the numbers and see if they're divisible by 3. For example, if I were to look at the number 123, well, 1 plus 2 plus 3 is equal to 6, and 6 is divisible by 3, so 123 is divisible by 3. 2 plus 5 plus 9 is 16. So that's not divisible by 3. I also see it's not divisible by 5. Is it divisible by 7? 259 divided by 7 would be 3, would be 21. And 5 take 1, 4, 9. Oh, look at that. 749. So this is 259 is equal to 7 times 37. And 7 is a prime and 37 is a prime, so this is equal to 2 squared times 7 to the first times 37. Like that. Okay? This brings up another interesting issue. If you may recall, let's see, in the last example I was looking at 259. And the question is it prime? So the question is what test do I have for determining primality? How do I determine primality? And here is the answer, okay? First of all, I want you to note that the first question I want to ask is what is the square root of 259? Now, you all may be running to your calculators, and you don't need your calculators here. Watch how I'm going to do this. First of all, I note that, let's see, 20 squared is equal to 400. So I know the square root of 259 is less than 400. I know that 15 squared is equal to 225. 16 squared is equal to 256. Now we're getting close. So I know that the square root of 259 is somewhere between 16 and 17. Notice how I did that without a calculator. Now, to check whether 259 is prime or not, I must consider all primes up to 17. So let's consider that for a second, and I'll explain why I have to only consider them up to 17 in a second. But what primes are there up to 17? Well, there's 2, there's 3, there's 5, there's 7, there is 11, and there is 13. These are the only primes, okay, that are between 1 and 17. To determine if this is a prime number or not, I have to determine whether any one of these divides 259. If one of these divides 259, clearly this is not a prime number. But if none of these divide 259, then I could conclude that 259 is a prime number. Let me formalize that for you. Okay? This is very important. And I'm going to say theorem. Okay? I'm going to say n is composite if and only if n is divisible by some prime p where p is less than the square root of n. That's very, very important. Okay? And the proof of this is actually pretty simple. Suppose false. Okay, now we know I'm going to say uniquely factor n in other words, let's come over here and say n is equal to some p1 to the alpha 1, p2 to the alpha 2, all the way up to some p sub k alpha k. Remember, we're saying that this is the unique factorization of n, and we're supposing that this is false. Now, if this is false, that means that each one of these is greater than the square root of n. Well, if each one of these is greater than the square root of n, then just multiplying any two of them together is going to be greater than n. Does everybody see that? So the conclusion we make is that at least one of these has to be less than the square root of n. Therefore, if n is a composite number, it must be divisible by some prime that is smaller than the square root of n. Let's just think about that again. Okay, so for example, if n is equal to, I don't know, 3089, that's a pretty big number here. What I am saying is if n is composite, then n is divisible by of prime p less than the square root of 3089. What is the square root of 3089? I don't know. 25 squared is equal to 625. 30 squared is equal to 900. 40 squared is equal to 1600. 50 squared is equal to 2500. Okay, 60 squared is equal to 3600. So we've got to find some number between here and here. What's 55 squared? Again, I don't know the answer to that. 25 carry the 2 is 27. 5, 27. So that's 5. That's 2 carry the 1, 0, 3. 55 is right there. What about 56? 6 carry the 3 is going to be 33. That is going to be 0. Carry the 3 is 28. And we can see that this is 6, 3, 1, 3. So we have to check all the primes, okay? Less than 56. Okay, and we can see that that's not a particularly long list. 2, 3, 5, 7, 11, 13, 17, 19, 23, let's see, 25, 27, 29, 31, 33, 35, 37, 39, 41, 43, 47, 49, 51, 53. That's it. So I would have to check to see if any of these numbers here. Phone is ringing. Excuse me. Okay, we answered the phone and we're back. So you can see that to check whether this is a prime number or not, we need to check all of these numbers right over here, which is not that many. This process has a name. It's called the sieve. Let me write it up here. The sieve of, and I'm probably going to misspell this, so your homework is to check my spelling. Eratosthenes, I believe, is the correct spelling of it. Eratosthenes was a Greek, and this is a way for actually generating and checking for prime numbers. So your homework, among other things, is to check the spelling of this name right over here. There's just one other, well, there are a couple of other things I want to state here. So some properties about prime numbers. I want to say if P divides A times B, and P doesn't divide A, then P must divide B. And I'll just ask you to think about that. Here's another thing I want to talk about. I want to talk about this thing called the greatest common divisor. Okay, so for example, and I think you've all seen this, for example, the GCD of 26 and 36 is equal to 2, because 2 divides 26, 2 divides 36, and if A divides 26 and A divides 36, then A is less than or equal to 2. In other words, the greatest common divisor of any two numbers is a number that divides both of the numbers, and it's bigger than any other number with that property. Okay? Now, how do you find the greatest common divisor? And we're going to talk about how we find the greatest common divisor several ways, but one way to find it here is I want to talk about, I'm going to look at the prime factorization of this. And 26 is equal to 2 to the first times 13 to the first. And 36 is equal to, let's see, that's going to be 2 squared times 3 squared. Now the way that I find the greatest common divisor, it's a very simple trick. What I do is I look at this unique factorization over here, and I first have to find what primes do they have in common. And the primes that they have in common over here is just the number 2. Then the other thing I have to do is I have to come over and I have to look at the exponent. When I come over here and I look at the exponent, I look for the smaller one. And the smaller one is this one right over here. So that says to me that the greatest common divisor of these two numbers is 2 to the first, right over there. Let's look at another example, maybe a little bit more complicated. So I come over here. Let's consider the GCD of 48 And I hope I'm going to make up a good number here. Let's try 92. Okay, well, 48 is equal to, well, that's 4 times 12. Well, that's 2 times 2. 2 times 6. Well, 6 is 2 times 3. So that's 1, 2, 3, 4. That's equal to 2 to the 4th times 3. 92 is equal to, oh, look at this. Okay. That is equal to 2 times 46. Well, 46 is equal to 2 times 23. So this is equal to 2 squared times 23. So I come over here, I've got 2 to the 4th times 3. And over here, I've got 2 squared times 23. Well, the primes that are in common here is just a 2. And the smallest exponent here is a 2. The greatest common divisor here is 4. Okay?